So section 3.7 talks about rates of change in the natural and social sciences. The good news for you is that we're doing this as opposed to exponential decay, exponential growth type of problems. So it is nice, but let's just work with problem number what I call 1-ish. And what I'm doing is I'm changing just the numbers of one of the problems in your homework, or just a little bit of it, so that it's a little bit friendlier. And here's all the questions. There's a lot of stuff that they ask us about this. So, particle moves according to the law of motion, S equals f of t. So in our case, I define that as t cubed minus 6t. I want to find a lot of different things here. So starting with the velocity. Well, if this is how your position, then what's going to tell you the velocity? First derivative, right? The derivative tells you the change in position, and your change in position is the velocity. So, all right, well that's a pretty easy one, right? So part A, S prime of t equals v of t, right? The derivative of the position function is your velocity, and that I'm not even going to bother asking you for it because I think that's pretty easy. S of t equals 3t squared minus 6. How about 12t? God, 12t. Nothing like, yeah. Yeah, that's not a good start to this video here. All right. Well, let's see if I can screw up the next one then too. What's the velocity after 1 second? How would I find that? The velocity after 1 second. Yeah, plug in v of 1. V of 1 is going to be 3 times 1 squared minus 12 times 1, which is negative 9. Do they give us units here? I don't see any measured in feet per second. So this would be feet per second. What do you suppose that's saying about this? Beyond the fact that it's moving 9 feet per second, what do you think the negative is saying? Yeah, it's moving down, or it's moving in a non-forward direction. It's moving backwards. So let's keep going. When is the particle at rest? That's an interesting question. When is the particle at rest? Set what equal to 0? S or V? V. We want to know when the velocity is 0, because when the velocity is 0, it's stopped momentarily, but it has stopped. So we want V of t equals 0, which is 3t squared minus 12t. Personally, I would hope that you factor this. You could pull out the quadratic formula. That's like squirrel hunting with a bazooka, but it'd work. Factor out the 3t that leaves behind t minus 4, and hopefully you can look at this and just know, all right, where t equals 0, or what makes v equal 0 at what values of t. So what are our solutions here? 0 and 4. So okay, 0 and 4. Nice. It says, when is the particle moving in the positive direction? So what's that going to mean? So, what is it moving in the positive direction? What has to be greater than 0? Yeah. The velocity has to be greater than 0. So let's look at our velocity function. In fact, we've got it nicely, neatly factored here. So I know where the roots are. And the velocity function, if you were to graph this, is a nice parabola, right? And we're going to see where it crosses the x-axis at 0 and 4. Now, I'm not going to draw necessarily a wonderful rendering of this, but it has to look something like this. You've got a parabola that crosses the x-axis here and here. at 0 and 4. So to the left of 0, the function is positive. Between 0 and 4, what's up with the function? Negative, and then positive. So as far as when is it moving in a positive direction, well, that means that t is greater than 4, t is greater than 4, or t is less than 0. So for those time values, the function is moving in a positive direction. Now you could also write that with interval notation. It'd be this interval would be negative infinity to 0, parenthesis, union 0, or excuse me, union 4 to infinity. Quick question for you. Why am I using parentheses and not brackets? Why don't I include 4 and 0? Andrew? Oh, okay. Yeah, so why doesn't it include 0 and 4? Yeah, at these points, it's not moving, right? Right at 0, in fact, that was our problem just up above. At 0 and at 4, the particle is not moving at all. So it has to be other than 0 and other than 4. But yeah, you had a question as well? You know, I don't, let's see. They did put a little restriction on this now that you mention it. The t, it has to be greater than 0. But, I mean, t equals 0 is sometimes a reference point. So that it's like, okay, well, you know, in fact, one of the problems that we did later on, or that we're going to do later on in this section, I decided the year 1950 would be t equals 0. So that things before 1950 would be negative. Yeah. But as far as this problem is concerned, I think the book's answer would be just this piece of it right there. So good. Appreciate it. Anything else on this one while we're at it? Let's take a look at part E, which is asking us to find the total distance moved. So, okay. Well, for that, maybe it's helpful to look at this graph. Now, when this particle starts out, you know, if you want to think of its motion on a line, it starts out by moving to the left because it's moving in a negative direction. It has a negative velocity. And it keeps moving to the left until you get to time 4. So the question is, well, how far do you get up to time 4? What's your position at time 4? How could I find that? No. We actually don't need calculus for this one. Yeah, you just want to go back to your position function, right? This tells you where the particle's at. So if you plug in t equals 4, you can find out, well, where the particle is at time 4. And so what should have happened is that it should have moved to the left. And let's see that that's true. S of 4 is going to be 4 cubed minus 6 times 4 squared, which is 64 minus, let's see, what, 24 times 6, 144? Is that right? No. 96, my bad. 96, so I get negative 32. So it started out at time 0, and then at t equals 4, you're at a position of negative 32. Okay, that's how far it moved to negative 32. The problem itself is asking you how far it moved during the first 6 seconds. Well, what happens after t equals 4? The function starts, or the particle starts moving the other way, right? So it's going to keep on moving the other way until we get to time 6. So where is the particle at time 6? Yeah, you plug it in. So at s of 6, we get 6 cubed minus 6 times 6 squared. And guess what? That's 0. So actually, I probably shouldn't draw that there. I should probably draw it here. Okay, so you're gone, and gone there. So here's what's happening with our particle. It starts out at t equals 0 here, and then moves to this point, t equals negative 32. And then in the next 2 seconds, between 4 and 6 seconds, it comes back to where we started. So t equals 6, s equals 0. So the question is, how far did the particle move? The answer is not 0. Because the answer has taken into account that you moved to the left and back to the right. So how far did it move altogether? 64. So you have to really look at kind of like the absolute value of that. Negative 32 plus another 32 gives you a total distance of 64. That's how far the particle moved in that time. Part F is just to draw the diagram that I drew here. Part G asks us to find the acceleration at time t and after 1 second. So how am I going to find the acceleration of this? Good. The second derivative. So v prime of t is going to be a of t. Let's go back up here. V prime of t is going to be what? Perfect. 6t minus 12. Okay. And then the second part of this is v prime of 1 or a of 1, which is negative 6. Now there's one last part of this, and it says, when is the particle speeding up? When is it slowing down? So, okay. To figure out that, which function do you think I should look at? Which acceleration, right? So, if you look at our acceleration function, a of t is 16 minus 12. The particle is speeding up when the acceleration is positive. If your acceleration is positive, then you're getting faster. If your acceleration is negative, you're going slower. Now, it's not talking about your velocity, it's just talking about the change in velocity. So, let's find the break-even point. The break-even point is when this is equal to 0. So, 6t equals 12, or t equals 2. Now, if you wanted to picture the graph of this, it's going to look something like this. You're going to have a y-intercept of negative 12 and an x-intercept of 2. So to the left of 2, is when you're slowing down, and to the right of 2 is when you're speeding up. So the last part of this, H, actually this is I. When's the particle speeding up? Speeding up for t greater than 2, and slowing down. T is less than 2, and if we're keeping, oh no, what? go. If you keep track of things and realize that the book says, well, we're working with positive values t, then it's just t between 0 and 2 would be where the particle is slowing down. Wow, that was a long problem. Don't worry, I'll only ask like 7 or 8 of those on an exam. All right. Yeah. Any follow-up on little parts of this problem? It was like I said, it was a long problem. So took a good page of notes. Let's keep going then. Let's move on to problem number 8. A much more doable and sane problem in terms of its length. So, 13. Let's get out problem number 8 for us. So a ball is thrown upward with a velocity of 80 feet per second. Then its height after t seconds is given by this function. What's the maximum height reached by the ball? This is kind of cool to be able to do this with you because in a college algebra class, this is a quadratic polynomial and you have to complete the square and all that stuff. But in calculus, it's going to be a lot friendlier. So let's start by recalling the function. It's s of t is 80t minus 16t squared. We want to know the maximum height. Let's think for a minute about the maximum height. When you throw something upwards, what's eventually going to happen? It's going to come back down, right? And in between the time when you're going up and the time when you're going down, something happens to your velocity function. Something we just dealt with just a moment ago. Velocity becomes, what's going to happen to velocity at that highest point? 0. Because for an instant, it's just going to pause. So the question is, where is that? What value of t? Well, first we're going to find the derivative, or not v prime of t, just v of t. V of t is going to equal s prime of t. S prime of t is going to be 80 minus 32t. Okay, well, that's not so bad. Now, if I want to know where this is equal to 0, we'll set it equal to 0 and solve. 80 equals 32t. 80 divided by 32, I think that's 2.5. Someone want to double check me on that one? 2.5? Good. So 2.5 seconds in, that's where you're going to have that maximum height. In fact, what is the maximum height? How are we going to find it? Well, we know when it occurs, but what is it? Yeah, you want to plug that into the position function. So s of 2.5 is going to be 80 times 2.5 minus 16 times 2.5 squared. Certainly want to do that one on a calculator. I'm getting 100. Is that what you guys are getting? Yep. Good deal. And the units there would be feet. So there's two questions you could ask. You could ask when it's at its highest, and that's after 2.5 seconds. And you can ask what the highest is, or your max height, and that'd be the 100 feet. So am I looking for the t coordinate / kind of the x coordinate, or am I looking for the y coordinate? And I'll try and be careful to point out exactly what I'm looking for. There's a part B to this as well. And part B says, what's the velocity of the ball when it's 96 seconds above the ground on its way up and on its way down? So that's kind of odd. But I guess the first thing we need to do is figure out, well, at what point point is at 96 feet above the ground. How can I figure out when this is 96 feet above the ground? Yeah, thank you. We'll set it equal to 96. So 96 equals 80t minus 16t squared. Personally, I would move everything to the left-hand side because that's going to make that negative 16t squared positive. And getting rid of those negatives is going to make your life a little bit easier than moving everything to the right-hand side. So 16t squared minus 80t plus 96 equals 0. Now this is a kinder, gentler math class. So let's do this as easy as possible. And I think Eureka is saying, you know what, the easiest thing to do here is to factor out the 16. Because that leaves behind t squared minus 5t plus 6. And that's looking a lot friendlier. Because I can factor what's in the middle. And even though I can factor it, I'm going to let Jeanette tell us here. How does this factor? Two things that multiply to 6 and add to negative 5. Thank you, negative 2 and 3. So these are the times at which the ball is 96 feet above the ground. Can someone interpret that for me? How come it's at the 96 feet above the ground twice? Yeah. It's a parabola. Somebody else said it. Yeah, it goes up and it comes down. So basically what's happening is it goes up and it goes down. You reach that maximum height here of 100, but on the way up and on the way down, you reach a height of 96 feet. So, in fact, yeah, do we solve for it? No. So yeah, no, let's see, would this be like 5 seconds? 0, 5 seconds. I think that's when that would be. In any case, let's finish this one up. I want to know the velocity when this is going up and when it's coming down. So I want to know the velocity at 2 seconds. So v of 2 is going to be 80 minus 32 times 2, which is 16. That'd be feet per second. And v of 3 is going to be 80 minus 32 times 3, which gives me negative 16 feet per second. What's the significance of that negative there? What's that telling me? Yeah, it's going down. Yeah, that's the significance of the negative there. So, nice. All right, problem number 8. Probably a little bit friendlier than the last one, but if there's some things on this that need clarification, let me know. Looking good there? Yay, awesome sauce. Let's look at problem number 14 next. And there's kind of a cool thing, a little connection I can build for you here between a couple formulas that you've memorized for years, but I want to build another connection here. So as a stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60, bless you, centimeters per second. Let's just stop here. What I'm going to need to deal with as part of this problem is a formula for the area of a circle. So this is problem 14, but you know we're gonna do a little bit of a side here. What's the formula for the area of a circle? Now, come on, make me look good. Yeah, all right, there you go. Pi r squared. Now, let's think about the derivative. when you differentiate something, it tells you how something is changing. So if I found the derivative of this, if I found a prime of r, it's telling me how the area of the circle is changing. Now imagine a circle expanding farther and farther outward. Okay? How is that changing? Where is that change taking place? It's taking place at the edges. At the edge, at the outside. If I differentiate this with respect to r, what do I get? 2 pi r. Do you see a connection here? What's 2 pi r? That's the circumference of a circle. Oh, cool. So one's the derivative of the other. Now, let's go a little further. Let's bump it up into another dimension. The volume of a sphere, I don't expect you to have this one memorized yet. All right. Is 4/3 pi r cubed. Now, think of a balloon being blown up, and we'll be doing this pretty soon. It'll be your favorite problems. When you're blowing up a balloon, what's changing? Where is it changing? That change is taking place right on the surface. So let's figure out what the derivative here is. S prime is going to be what? Or V prime is going to be 4 pi r squared. And this is the formula for the surface of a sphere. So again, it's the derivative. And you can keep on playing on this game. It's amazing. Even though you can't see these objects, we can calculate the volume of a sphere in 4 dimensions and in higher dimensions. And it's like really bizarre. It's kind of fun. But this is where I'm going to stop here, because really all we need is these two right here. So, all right, the rest is just good bonus material. Let's go back to the problem. It says a stone is dropped in a lake, creating a circular ripple that travels outward at a speed of 60 meters per second. So we have A equals pi r squared. And what they're telling us is the rate of change of the radius. So it's dr by dt. That's how the radius is changing, is 60, or was it centimeters per second? I want to get the units right. Yes, centimeters per second. Thank you. Centimeters per second. Find the rate at which the area within the circle is increasing after 1 second, 3 seconds, and 5 seconds. So, well, how do I find the rate of change with respect to the area? Well, I'm going to differentiate. But we got to be careful here. I'm going to differentiate not with respect to A or R, with respect to time. So dA by dt, and that's going to mean over here, what's going to happen when I differentiate this with respect to time? Ooh, bonus points here. Somebody tell me. Make me look good. We're going to have a dr dt term. Ah, excellent. You got to do it implicitly, right? So we got to use a chain rule. It's going to be 2 pi r dr by dt. So you got to use the chain rule on that one and differentiate implicitly, because I'm not differentiating with respect to r, which would be nice because then this term wouldn't be here. I'm differentiating with respect to time. Okay. Let's see. They want to know how this is changing at several different times. At time equals 1, time equals 3, time equals 5. So how is the area changing at different rates, or at different times? Well, dA by dt here will be 2 pi, let's see, what radius? Uh-oh. I think I got a little overzealous on this one. 60. Oh. Okay. After 1 second. Yeah, after 1 second, the radius is going to be 60. So 60. I guess that kind of gets lumped in together here. I'm a little bit bothered by that. I was dr by dt. Radius is 60. Let me just look, because part of this feels like stuff that's a little bit ahead where we're at. Let's see. Yeah, pull it up on Slater. Find the rate at which the area is changing after 1 second. Go ahead. Circle channels outward. 30. What can you conclude? Yeah, because the way we're doing it here, but I think I need both of these, so I'd end up multiplying like twice. I'd have the r, I have to figure out the radius, and I have to use the dr dt. So at t equal 1, after 1 second, it's traveled outwards 60 centimeters, and then you have this dr dt term, which is again 60. So we'd have 3600 times 2, we'd have 7200 pi. Is that what they're coming up with, or are they doing?
You have to add a t, so it would be 2 pi times 60t times 60.
2 pi times 60t. Well, t is 1 there, so we kind of got the 1 here.
Right, and that would be the answer to
First part, right?
And then the second time you have to add 2.
Yeah, exactly. So for the second one here, for dA by dt, it's 2 pi. This time, after 3 seconds, how far is this traveled? What's r after 3 seconds? 180. Well, what's going on is that, how comes this keeps on fading out? There we go. What's going on is that we need to figure out what the radius is at these different times. So that's what I'm doing right here, is because the radius is part of this formula, I have to figure out, well, what's the radius after 1 second? And it's 60 centimeters times 1. In other words, r is 60 times t. That's what we're using. So 60 times 1 gives us 60. 60 times 3 gives us 180 times dr by dt, and boy, I don't have that one. 10,080, 20,160? I don't know. Let's see. 20,000, 1080 times 60 times 2. 21,600, yeah, thank you. 21,600 pi. The last one, t equals 5. So dA by dt is 2 pi. What's the radius when t equals 5? What should I put in here? 300. dr by dt stays the same, so that's 60. So it's 1,800, 36,000? 36,000 pi. Now this is the change of the area with respect to time. So that would be in feet squared per second. Feet squared per second. Feet squared per second. Oh, is it in centimeters? Oh, crap. Great. All right. There we go. Centimeters. Thank you. Centimeters. centimeters. Yeah, it was a little bit more tricky than I'd really wanted because of this term here didn't disappear. A couple more to finish out this section. Problem number 18. I think this one, in fact, I know this one's going to be a little bit more reasonable to deal with. We've got a tank that holds 5,000 gallons of water. It drains from the bottom of a tank in 40 minutes. Torricelli's law gives the volume of water remaining in the tank after T minutes, and it's this formula. It's T between 0 and 40 minutes. We want to find the rate at which the water is draining from the tank after 5 minutes, 10 minutes, 20 minutes, 40 minutes. At what time is the water draining the fastest? So, what's your intuition tell you? When's this going to be draining the fastest? When's there going to be the biggest outflow? 5 minutes, yeah. Because when you got more water, there's more pressure to expel that water. So that's what we would expect. We're going to differentiate this with respect to time. So let's copy down that formula. It's V equals 5,000, 1 minus 40T, all raised to the second power. So problem number 18. V of T. Thank you. 5,000, 1 minus 1 over 40T squared. So the rate of flow is going to be dV by dt. dV by dt. Let me try that again. So I want to differentiate this with respect to time. You could, if you wanted to, square this out, distribute the 5,000, and just differentiate it term by term. But we got a chain rule. And chain rule is going to be easier than all that. So let's see if we can apply the chain rule here. It's going to be the derivative of the outside. So 2 times 5,000 is going to be 10,000 times 1 minus 1 over 40t to the first power. So that's the derivative of the outside times the derivative of the inside. The derivative of the inside is pretty easy. Got to be careful. It's going to be negative 1 over 40. And you need that negative. So the negative here and the 40 here, it gives me negative 250 times 1 minus 1 over 40t. And that's my dV by dt. Now they ask for the rate of flow at 5, 10, 20, and 40. Here's what I do. I wouldn't be inclined to type that in by hand repeatedly. So what I'll do is I'll plug that into my calculator. Plug that into Y1. I'll get rid of a couple other formulas there. So negative 250, parentheses, 1 minus, I'll just do it as this, x divided by 40, like that. Now hopefully you have your table set up correctly. So second table set, you should have the independent set to ask. Then you just go right to the table. Delete all the values there and type in the ones that you need. 5, 10, or was it 20 and 40? Yeah, 20 and 40. Of course, at 40, I don't expect anything left. Now, if it's imperative that you get these correct down to the nearest decimal, cursor over to the y value and come up, and you can see that it's not really negative 218.8, it's regular negative 218.75. It just doesn't have enough rooms there, so it rounds. So back to the question in the book. At what time is the water flowing out the fastest? Well, like Tao suggested, at 5 minutes. At what time is this flowing out the slowest? Yeah, at 40 minutes. So in general, what's happening to the flow of water as time progresses? Yeah, it's decreasing. All right, it's not coming out as much. What do you think the negative reflects in all this? Yeah, you're losing water, right? The volume is decreasing, right? That's what's happening here, is that you have water flowing out of your tank, so the amount of volume is decreasing. Okay. Yeah, she is. Any follow-up on that one? Let's take a quick look at problem number 20A. This is a nod to someone we studied earlier in this course, Isaac Newton. 20A. So in case you ever felt the compulsion to calculate your gravitational effect on somebody else, then you can do it with this formula. F of R is G times capital M times little m divided by R squared. Wow. What on earth is that? That's Newton's Law of Gravity. And I'll just plop this down here real quick. We're just going to look quickly at the first part of this. Newton's Law of Gravitation says that the magnitude F of the force exerted by a body of mass m on a body of mass m, big M and little m, where G is the gravitational constant and R is the distance between the bodies. Find dF dr and explain its meaning. What does a minus sign indicate? So that's all we're going to work on is that first part. We're going to find the derivative of this with respect to R. So when we differentiate this as a function of R, what's that going to mean about G, little m, and big M? They're constants. Yeah. So if you're going to differentiate this and realize that these are constants, do you really want to use the quotient rule? No. And for my viewing audience, everyone's shaking their head vigorously. No, we don't want to use the quotient rule. So we'll rewrite it as G, big M, little m, times what? R to the negative 2. So, it's all right. So that is all just a constant. So we can just kind of like leave that alone, and the negative 2 comes out in front, so F prime of R is going to be negative 2 times G, M, little m, R to what power? Negative 3. So negative 2 G, M, M over R cubed. Now, first of all, what's your intuition say about the force of gravity? As you move farther apart from, say the sun or another object, what's going to happen to the force of attraction, the gravitational force between those two things? It's going to decrease, right? And we actually see that. That's what the negative is saying, that force is decreasing because we have a negative here. This is all positive. The radius is going to be positive. So we have a negative times something positive. Overall, this is going to be a negative quantity. So as you increase the radius, you're going to decrease the force. And that's the conclusion that they wanted you to get here. Yay. And that's all we're going to do with this one. Well, remember he was home from Cambridge when Cambridge was shut down by the plague. So he was hanging out on the farm and certainly wasn't into farming. His mom found that out the hard way. A couple times she had to pay the neighbors for damage to their crops because pigs from the Newton's farms would go over to adjacent farms and have themselves a good time. Okay. Last one. Problem number 28. And if those of you are really motivated, I can send out the link on Desmos. I didn't. says the table shows the average age of first marriage of Japanese women, how it's varied since 1950. Well, I was kind of curious about the average age of women in the United States and how that's varied since 1950. So I dug up some data, and if I send you out the link, then I think this, yeah, there's my source. So however good that is, great. It says, use a graphing calculator or computer to model this with a fourth degree polynomial. So that would be this thing right here. And the nice thing is that with Desmos, you can just type this stuff in, and it'll actually find a fourth degree model. In fact, let's plot it. Does it look like there's a change in the average rate at which women get married through the years? This is 1950. That's my year zero, right down here. So year zero was 1950, and the data goes up to, I think, about 2018. Yeah, there you go, 2018. Yeah, question?
So how would we find it
On a graphing calculator? I wouldn't make you do this on an exam. I'd give you the equation. So, in fact, when you type it into Desmos, one of the things you get is the equation. So, your model is the form of ax to the fourth, bx cubed, cx squared plus dx plus, I chose f for reasons dealing with Desmos, but you could do an e. And here's the model. Well, looks like a pretty good model, don't you think? Mathematics is actually really good at modeling things. I mean, it's not perfect, but you're summarizing an entire table of data with just a polynomial. So the question that they ask after this is, use part A to find a model for A prime. Estimate the rate of change of marriage for women in 1990. How fast is that changing? So let's take a look here. Got the model down at the bottom for us, and it's kind of ugly. I won't lie to you. It's right here. You've got this one right here. Let's see if so we'll do y equals negative. No, it's positive. Is that positive? Yeah, it's positive. 9.44 times 10 to the negative 7th. That really means you got 6 zeros and then the 944. 0.000000944 times x to the fourth. They're just not friendly numbers. And then there's the model for x cubed. So negative 0.0001596 x cubed plus 0.009722 x to the second minus 0.114253x, and finally, last but not least, plus 20.4309. There you go. Now, it doesn't work out nice and even. I won't pretend that it does work out nice and even, but let's just use our mind a little bit and figure out what we would do to answer a couple questions. The derivative, even though it's ugly, I think we could find it. But then it says, estimate the rate of change of marriage for women in 1990. So what would you do if you're asked to find the rate of change of date of marriage for women in 1990? Yeah, you plug in 40 into y prime. So x equals 40 into y prime. So Yeah, you have to find y prime. So now, part of what might kind of like throw you a little bit is, why is this leading coefficient so small? I mean, you got a really, really tiny leading coefficient. It's like, well, why bother? But you have to remember that this is the coefficient of something to the fourth power. So, for instance, in the year 2000, when we raise 50 to the fourth power, that's going to be a significant number. That's going to be like 6.25 million times this number. And that'll start to make an actual contribution for large numbers like that. But I'll let you finish this up for your homework problem for number 28. And you can do that instead of problem number 27. So for homework, try 1, 5 through 9, 13, 15, and 27, or 28-ish, the way we did it. But finish up one of those.